different vendors created their own protocols for the data exchange. So it is segregated as the high-speed protocols and the low-speed protocols. Some of the high-speed protocols are JESD, AXA, and USB, and some of the low-speed protocols are I2C, SPI, UART, and so on. Today we are going to discuss about the I2C protocol. So what is an I2C protocol and where we use it? I2C, the name itself says it is an inter-integrated circuit, means like inter means the communication between the two different things. Okay, so that's why it is called an inter-integrated circuit, because this interface is this protocol is mainly used to establish a communication between the two different ICs. And this I2C protocol offers 4 operating modes, like for the data transmission, ranging from 100 kilobits per second to 3.4 megabits per second. Like many of the IC vendors in this world use this I2C interface because the hardware complexity of this I2C is very less. Let us say your personal computer itself is having around 8 chips, which is having an I2C interface. Because the main ambition of this motherboard is to make small compatible devices. So they try to decrease the hardware complexity. That's why this protocol is very famous. So what is an I2C bus? I2C bus is nothing but the combination of the two lines, which are called as the serial data line and the serial clock line. As we already know that I2C is an inter-chip communication protocol, there exists a controller and a target. Controller is nothing but a master.
Sir?
Yeah.
Sir, what is a bus, sir?
A bus is like concatenation of the few signals is called a bus. Like so for easy terminology, like for example, if you are creating
for example, sir.
Sorry. Hello.
Yeah, you can continue.
Okay, like the bus is nothing but a combination of the few signals. Like all the English letters are commonly called as alphabets, right? So in this electronic world, all the signals which are related to one family, they are called as bus. Okay, that's why we call AXA bus, I2C bus, SPI bus. All the signals related to SPI are commonly called as the SPI bus. Okay. So as we already know that I2C is an inter-chip communication protocol, there exists a controller and a target. So why I'm using here is a controller and a target convention means like in this era, like these days, everybody is not using this master and slave concept. All are using this controller and target in the industry. That's why I just want to let you know the master is replaced with the controller and the slave is replaced with the target. Okay. The controller could be a microcontroller or processor, and any IC can act as a target if it has an I2C interface. Okay, so in your laptop, you have one processor, and you have many sensors. Like let us say, for example, a temperature sensor, which is used to turn on and off the CPU fan. Okay, that sensor itself is having an I2C interface. Like that, you have so many ICs in the motherboard itself, which is having I2C interfaces. So there we have only one controller, that is called the processor, and remaining all the ICs are called as the targets. Okay, sorry. So this is the meaning of that sentence. A single controller can interact with several targets, meaning it can use the same two lines to speak with them all, but not simultaneously. At a time, it can communicate with the only one target. So at a time, you have only one controller and one target communication. SDA line is bidirectional because the controller uses the SDA line to send and receive data to and from the target. So you will have this controller and you will have a target over here. And you have one SDA line and one SCL line. This SDA line is bidirectional, means it can send the data to target and it can receive the data from the same line using the same line from the target. Whereas SCL is only one directional from the controller to the target. the clock is provided by the controller to the target. That's why it is output from the controller. As the controller itself sending the clock along with the data, this interface is called the synchronous interface. Okay. So this is the one which I'm talking about earlier. So here we have only one microprocessor, one microcontroller, and we have a lot of different ICs which is having an I2C interface. So all these are interacting with this processor with using only these two lines, SCL and SDA. So now we shall talk about some I2C terminals which you hear very frequently. One of the term is open drain. Okay. So every GPIO can be configured in the two modes, not two modes. Like I'll just let you know two modes only because you'll get some clarity on that. So one of the mode is push-pull mode. Okay. And another one is the open drain mode. So what this push-pull mode means, we can just change the states of the signal from 0 to 1 or 1 to 0. That means it can drive 0 and 1 both. Whereas coming to this open drain, it can drive 0 and the floating state. Floating is nothing but Z state. Okay. So it can write 0 or else it will not write anything. It will just leave that signal. Meaning that, so let us take this image. So here you have a FET transistor, right? So this logic will write only 0 to this FET transistor, or else it will write 0. Means it will not write anything to this FET transistor. Okay. So now what is pull-up resistor? So how this I2C protocol exploited this open drain functionality means, so they are having one single line which is connected to VCC using one pull-up resistor. Okay. So this line always, this line's logic is always one only. Okay. Now they are connecting one controller over here and one target over here. So this controller and this target will see this line as one always. Okay. So who will change the state of this line means, so when initially this will be one, this will be seen as one by both by this controller and the target. So let us say if the controller wants to write something this to target, it will just send the clock and data to the target, right? So during the clock transmission, so whenever the clock is 1, the controller sends just G. G means it will not write anything over here. So if it not write anything means what the state of this wire, this is 1. So at the time this target will see this as 1. Okay. So whenever this logic wants to write 0, it will write 0 over here, and this FET will get activated and this will get dropped to the ground. So here now what is the state of this line? It is 0. So this target will see this line as 0. So there the transition will take from 1 to 0. So whenever it wants to write 1 again, it will not write anything to this line. It will make it as 0. So this will get deactivated and this will pull high again. So again, after 0, it will go high again. So in the same way, the SDA also works. So did you are you guys with me? Did you get what I'm trying to say? Hello.
Yes, sir.
Yeah, if you have any doubts, please let me know.
Sir,
Okay.
can you explain once again, sir?
Okay. Sure. So let us take one wire. You imagine a wire over here. Okay. Just a regular wire which we use in our home. Okay. So you have two boxes over here. This is called controller and this is called target. Okay. Now, whenever we have some, let us say we have something to read over here. Okay. Just we are reading the values of this line now. Now it will show 0 only because nothing is there on this line. So the both will read as 0. So now what I'm doing is I will take a resistor I will take a resistor. I will connect over here, and I will connect to some 3.3 volt supply, power supply. Now I will read again over here. Now I see the logic 1 over here. Okay, are you guys clear with this point?
Yes, sir.
Yes,
Okay.
sir.
So now the target is seeing this line as 1, and the controller is seeing this line as 1. Okay. Now let us say we have some logic over here, and we have a one FET transistor. This FET transistor is connected to this this line only, the same signal. Okay. Now whenever this logic writes 0 to this FET transistor, okay, all this voltage will get dropped to this ground. Then when we read with this instrument again, you will see 0 over here. Are you getting my point? See, whenever this logic writes 0 over here, this is VCC. Okay, so whenever we write 0 over here, this transistor will get activated. Let us imagine this as a one. This buffer as a reading instrument, one of the reading instrument. Okay, whenever I'm not writing anything to this transistor, it is in the off state. So at the time when you do a read command over here, it will read it as a 1. Okay, because this VCC will be seen as 1 over here. When you write 0 over here, this transistor will get activated, and this voltage will get dropped to 0, because this is the closed circuit right now. Are you guys with me?
Yes, sir.
So if you do a read command over here now, this will read as a 0. If you don't want if you don't write 0 over here, if you put it as in a no connection state, then you will read 1 over here. If you write 0, this will get activated and you will see 0 over here. Should I repeat again, or I'm just making confused?
Fine, sir.
Fine, everybody, or should I repeat? Because this is the only, if you want to me tell very clearly, I can tell you. Because if you don't understand this, you will not understand the I2C completely. If anyone have, I can take one more session also. That's fine for me. If you guys listen, if you are not good with this, I will explain again.
Sir, please repeat one more time, sir, please.
Okay. So let us imagine a regular wire. Let us imagine a regular wire. Okay, this is a regular wire which in our house, how we connect all the our electrical things. This is treated as a regular wire. Okay, and now you are connecting two boxes to this wire on both the ends. Okay, one of the box is called as controller. Okay, just don't call it as a controller also. Just call it as a box 1 and box 2. Okay, and you have one instrument in both the boxes which can read the state of this end. So initially I'm doing the read of this point using this instrument. So on the both sides I will read it as a 0 only, right? So here is 0 and here it is 0. So now what I'm doing means I'm using one resistor, and I'm just connecting this wire and a VCC with a 3.3 volts. So now if I made a read command over here at this end, I will read that port as 1. Okay. As this resistor is connected to the 3.3 volts, that's why we called as a pull-up resistor. Okay. That's why this is called a pull-up resistor. Now what I'm doing is I have some logic over here. Okay, the capability of this logic is it can write 0 or else it can write 0. Z means it can write 0 or it can be in the floating state. That is the only capability of this logic. It can't write 1. Okay. I have a FET transistor over here. Okay. So now this FET transistor, now this logic is writing Z to this FET transistor. The same circuit is up here this side also. Okay. So whenever I write Z, if I read this point, it will be 1. Okay, because this transistor is not activated and this is the open circuit. Okay, this is the open circuit. That's why using this reading instrument, I'm reading it as a 1. Now what I'm doing means I'm at this point the logic state is 0. Okay, now what I'm doing means I'm writing 0 over here. So when I write 0 over here, this transistor will get activated. So when this transistor is activated, here we are getting a closed loop. Okay, now if I read at this point, it will be read as 0 only. Are you clear with this point?
If the transistor is of N type or P type, it depends on the kind of transistor. If it is
We are
P type,
using NFET. We are using NFET over here.
if NFET, then in case of if we are providing 0 at the gate, then it is also in off condition. It should be in off condition if we are providing 0 at the gate. If it is P type, then it will activate.
Oh, maybe I'm. Give me a second. Okay, I'll just confirm later what kind of transistor is exactly. Okay, now let us. Sorry for that. Now let us think in that way. So whenever we apply 0 over here, this transistor will get activated, and here it will form a closed loop. Okay.
Okay.
So
Okay.
whenever it forms a closed loop, so when we read at this port, it will be read as 0. Okay. So did you understand this thing, how it got?
Yes, sir.
Like everybody is clear with this?
Sir, how it is reading as 0, sir? Because both the nodes are connected to same VCC. So how it will be reading 0?
So see, like if in the electronic device and circuit, some subject will get right. So whenever we have a closed loop over here, okay, there will be no voltage that here, and it will be read as 0.
Okay, sir. Because
Okay.
and that node also connected to VCC only.
Yeah, that node also connected to VCC.
That it will the potential will be like 3.3 volt for 1.
Yeah, potential. It will be 3.3 volts for 1. So whenever it forms a closed loop over here, this complete voltage will drop to 0 at this point, because it is forming a closed loop over here, right?
Okay.
Okay. I'll just go through it and I'll just clarify you very well later. But sorry about that. Just for now, you just think it as like that, okay?
Okay, sir.
So everyone is clear with this? Just later, I will just go through this transistor and this voltage drops very well, and I'll just come back to you. The main thing is how it goes 1 and 0. Have you guys got that point?
Yes, sir.
Okay. So the one which I explained in the other slide is this one. Okay, so whenever you write 0 here, this transistor will get activated, and here the closed loop will form, and this port will be read as 0. Okay. that is the open drain and the pull up register. The start is the start command, and we have here in this controller and target concept. Controller can only initiate whether it is a read transaction or a write transaction. Okay, so that's why during the initial transaction it will let the target know whether it is a read command or the write command, and later target address. So what this target address means? See, here you have a lot of ICs, right? Every IC will have a unique address. Okay, so let us say at some instant this microcontroller wants to talk to this LED blinkers. It will just send the LED blinker address and it will communicate with the LED blinker. Later at some point of time it may talk to this LCD driver also. So every target will have a unique address, and that address is called as a target address. And coming to the acknowledgement, acknowledgement is nothing but, so when there is a successful transaction, the target sends acknowledgement to the controller, and NAC is sent, like NAC means when there is an unsuccessful transaction, NAC signal comes into the picture. And what is the target register address means? Let us take an example of a GPIO expander. So what is this GPIO expander means? Some of the microcontrollers will not have some enough GPIOs. So at that point, what the designers will do is they will use some of the GPIO expanders. So using two GPIOs, like using this, let us say this is a microcontroller, and this microcontroller is having two GPIOs. These two GPIOs will be connected to an IC, which is called as a GPIO expander. Excuse me. This GPIO expander will have 8 GPIOs. Okay. So GPIO means we can configure it as an input or output, right? So we can configure all these 8 GPIO, all these 6 GPIOs to be input or output. So to configure them as input and output, we need one register. Okay, that is called configuration register. And if it is output, we have to write something to this GPIO, or else if it is input, we have to read something from this GPIO. So that is called a data register. Okay, so let us think this IC is having only 2 registers. Okay, let us say we have one more register also, which is sends the output strength, if we configure it as a output, like what is the output strength of that particular signal of the GPIO. So we have total 3 registers. One is configuration register, and the other is the data register, and the other one is the output strength register. Okay, so totally we have 3 registers over here. So whenever the controller wants to configure the configure the ports as outputs or inputs, it has to write the configuration register, right? So the configuration is register 0, data register is 0, register 1, and whereas the output strength register is register 3. So 0, 1, 2, 3 are called as the target register addresses. Okay. Does anyone have any doubts?
Then repeat it once again.
Okay. So let us say we have one microcontroller. That microcontroller is not having enough general purpose inputs and outputs, GPIOs. Okay. So then what we can do means we can bring any IC which is called as a GPIO expander. Okay, means that IC can use 2 of these microcontroller ports, and it can bring the 8 GPIOs. Means these 2 lines, it is like a DMUX. Okay, it is like converting 2 pins to not exactly like DMUX. Like using these 2 pins only, it can create 8 GPIOs. How it is creating means, so here we are having 3 registers. Okay. And let us say we have only 4 GPIOs over here. And these registers are of 4-bit wide. Okay. So these two lines are the GPIOs of the microcontroller. Okay. Now what we are doing means we are using these two lines as for I2C interface. So one of the GPIO is called SDA and the other one is called SCL. And this IC is also, this is the GPIO expander IC. This IC is also having, this microcontroller is also having I2C interface, and this IC is also having I2C interface. Okay. So using this SDA and SCL, we configure these 3 registers, register 1, register 2, register 3. One register is called as the configuration register. Okay. So what is meant by the configuration register means, so what is the state of this GPIO, whether it is the input or output. Okay, whether it is the input or output can be decided using this configuration register. If we write one, let us say this 0th bit belongs to this GPIO, the LSB belongs to this, and MSB belongs to this GPIO. Okay. So whenever we write one over
At
here,
the same time, it will behave like an input or output, or same line will be used
No.
as an input or output.
at the same time, not like at a time you can use it as the only input. If you let us say in the minute 1 you are using it as a input. Okay. In the next minute, if you want to use it as output, you have to configure this register using this interface.
Okay.
Okay. Did you get my point?
Yes, sir.
Yeah. So you can change the state of those GPIOs in the runtime. That's why we are using this I2C protocol. So this register 1 is the configuration register, and this register 2 is if it is output or input, we have to, if it is output, we have to write something, right? So what you want to write to the GPIO will be written into this register. So 2 is called data register. When this GPIO is input, you have to read the GPIO, right? So then you have to read this register. Okay. And coming to the register 3 is the output strength register. Means like whenever you are using this GPIO as output, to change the current strength of the GPIO, you can use this register to change the current strength. Like if the 0th bit is 0, the current strength is 2 milliamp. If the LSB is 1, the current strength is 8 milliamp, like that. Okay. Everybody clear with this thing? Hello.
Yes, sir.
Okay. So that is the target register address. Now we are having 3 registers, right? So 0, 1, 2 are called the target register address. Target data means I already told you, right? So if you want to write 1 over here to configure it as output, that is called the data. Okay. So that is the data of that register, data of the configuration register, data of the data register, data of the output strength register. Okay. That is the target data. And repeated start means like you will have a start command and a stop command. So what is meant by the repeated start means there will be a scenario where there can be the multiprocessor. So in the multiprocess scenario, so all the controllers will have the same SDA will be connected to all the controllers, same SDA and same SCL. So at the time, what happens means, so when one controller is using this SDA and SCL, and the other controller also wants to use the SDA and SCL at the same time, it will be in a very conscious state to take over those two lines. So they implemented a new feature to get rid of this. Like if I'm using the bus and my transaction is not done yet. So in the I2C, there will be
Just remove the person without any warning. Just remove the person without any warning.
okay. So in when there is a multi-master scenario, let us say there are two human beings and they want to use the same resources. I want to use a motorcycle to travel somewhere, and my destination is not yet finished. So I stop my bike in the middle to have a small break. So the other person is seeing me all the time whether I'm using the bike or not. So he's capable. If I'm not using that bike, he can take over the bike. Okay. So what that is nothing but is called whenever you want to send a you have 2 bytes to send in the data transmission. So there will be a start command and stop command. So usually how it would be means like first we send the start command and we send the data and we just send the stop command and we again start the transaction again. So during the stop time, what happens is the other master will come and take over the bus. To get rid of this, they introduced the repeated start condition. So if they want to send the second byte also, they don't send the stop command, they send the start command again. That is the meaning of the repeated start. You will get to know what is the use of the repeated start in a few minutes. Okay. So the start command and the stop command. So how the start command and stop command is sensed by the targets. So we have two lines, right? SCL and SDA. So initially those two lines will be connected to the VCC. So initially those two will be in the high state only. Okay, means high means logic 1 only. So whenever controller wants to start a transaction, what it will do means it will activate that FET by writing 0 to over here. Okay, so then what happens? This SDA will change its state from 1 to 0. Okay, but this SCL will be in high state only. Okay, for the SCL FET it will write Z only. So this will be high only. This state, like whenever the SCL is high and SDA is changing from high to low, this will be sensed as the start command. So all the time, all the targets, let us say this slide. So here all the targets are active all the time. Okay, they will be listening to the controller all the time. So whenever there is a start command, so all these targets will sense now. Okay, there's going to be a transaction now, and they'll start to listen to master, like listen to the controller to match their addresses. So every target will have a unique address, right? So every target will listen to the master now. Okay, there's going to be a transaction, and they are not aware of who going to be the target. That's why they will listen to the controller now, and this is the start command. So after start command, first I will show you just the waveform of the start
Hello,
and
sir.
stop commands. Yeah.
Hello. Sir, in this, there is no concept of ready or those kind of things.
No, there will be no concept of ready and everything. You can we'll have those ready, all those things in the AXA protocol. We'll not have any ready those things in over here. Okay.
Okay, sir. And this is a peripheral protocol, not on-chip protocol.
Yeah, this is a peripheral protocol. AXA is the SOC protocol. That is the on-chip protocol. That's why like I2C is the inter means between the two ICs, two different ICs. Okay. Let me give a good example to differentiate that. Do you aware of this Zinc FPGAs from the Xilinx or the Altera FPGAs?
So I've heard about those things, but I have not used yet.
Okay. So did you heard about of any of? Do you know any of the microcontrollers? Any of the
8051.
Not like those things, like the one ARM Cortex M4.
Yes, sir. ST micro nuclear.
STM32 microcontroller, any of those microcontrollers?
Yes, sir. Nuclear.
Yeah. So if you open the data sheet of those microcontrollers, you can find a buses over there. All are like APP buses and AHP buses. There everything is interconnected within a single die. Okay. So there what happens means the processor is from the ARM, whereas the STM microcontroller, what they do means they will take all the peripherals, this UART, I2C, SPI, they will take all these peripherals, okay, and they will take the processor from the ARM and they will integrate everything on a single die. Then they will use this APP, AHP protocols over there to communicate between these two. Did you get my point? Okay, let me show you one thing. Like you got a good question. Let me show you something. Everybody can see this picture. Hello.
Yes, sir.
So you see this chip name is called TM4C 123GH6PM. Okay, this is a microcontroller which is designed by Texas Instrument. So what these people will do means here if you see there is a ARM Cortex M4F processor. Can you see over here?
Yes, sir.
So if you see this, so what these TI people will do means they will buy this ARM Cortex M4 processor from the ARM. So using that thing, using that processor, and here if you see they have a different peripherals. Here I2C, UART, Watchdog, DMA, EEPROM. So they have a lot of peripherals. So how they are establishing the connection between these peripherals and this processor means they're using this bus, and those buses are called APP bus and AHP bus. Okay. So these are like the on-chip protocol. So this AXI and everything is the on-chip protocol. Means they are used to establish connection between the main processor and the different peripherals. Whereas this I2C is like external. Like this protocol used to communicate with the external world. This is not related to the on-chip protocol. Are you clear with this, or should I take another example?
సర్టిఫికేట్ మీద ఇస్తాం కదా స్లోగా ఉంది సార్.
Moria, just remove the Devi person. Who is Devi? Just remove that person without any warning. Just remove it. Completely block it.
Okay, it's fine. Okay, so you were comfortable with the example. Should I take a new example and should I tell what's the difference between this?
Sir, this is complete chip now. What you are showing.
Yeah, what I'm showing is a complete microcontroller.
Okay, sir. Okay, sir. So all means for communicating on chip, these are HB and APP protocols, and that you are trying to say.
Yeah, that's what I'm trying to say. If you want, I can explain you in detailed way. See here you have. Let us take I2C only one of the example. Okay. So here you have I2C, right? Wait, I think this image is not. Okay. See here we have I2C, like this is like I2C master or I2C slave. So how to tell that means? So this I2C can act as both controller and target. Okay. So how this I2C peripheral can come to know whether it can act as a controller or whether it can act as a target is decided by this ARM processor. So how this ARM processor is communicating with this I2C chip means it is using this AHP bus, AHP or APP. Sometimes they give both the buses feature based upon the speed. Okay. So now what this ARM processor is doing means this ARM processor is deciding whether this I2C should act as a controller or target using this one of the buses. Okay. So after this, earlier we discussed about the GPIO expander IC, right? So that GPIO expander IP will be connected to this I2C lines only. Are you getting my point now?
Yes.
So that is the external bus. Okay, wait. I'll let you know. Wait, give me a second. So don't take the TI anybody. Let us take you are creating one microcontroller. Okay. So whenever you wants to create a microcontroller, your microcontroller is very simple. Okay. That microcontroller has just one memory, just one processor, and just one I2C interface. That's all. That microcontroller have only 3 parts. So you are designing a microcontroller, and now what you are doing means your part is only integration part, means like you are concentrating on how to integrate these chips which were created by the other people. Let us say I am creating the processors, okay, and the other guy is creating the I2C ASICs. Means I2C ASIC means that can be act as a controller or a target. Uh, and the other guy is creating, like let us say Samsung is creating some memories. Okay, so what you did means you came to me, you took a processor and you placed over here, and you went to Samsung and you bought a memory, and you went to some other person and you bought I2C ASIC. Okay, now what's your question is like, okay, I bought all the chips, now how to connect these chips? Okay, so first of all, why are you creating this microcontroller? First of all, why are you creating this microcontroller means you have one IC and you want to bring up this IC. What is that IC means? GPIO expander. Okay. So now you want to configure this IC. Earlier we told, right, this IC will have 3 registers. One is configuration register, data register, and the other one is the output strength register. So if you want to configure these registers, you have to use I2C protocol only, because the manufacturer of this GPIO expander he created this IC using the I2C interface. Means it having two lines only. One is SCL and other one is SDA. So now you want to bring up this IC. So you are creating your own microcontroller and you bought one processor, one memory, and one I2C ASIC. Okay. So now what you do, you write some code to configure this in any higher level languages, and that code is stored in this memory. Okay. Now the processor wants to read this memory. How it gonna be read? So you have to create one interface now between this memory and this between processor. So for that purpose, you use one bus. That bus is like also one of the protocol, and that could be any protocol, APP, AHP. You know, all these protocols are like the cover up, like they are like wrappers. You know, everybody internally will have some connections, like everybody will have some different connections, but coming to the outer world, they will show to the outer world, you can use my chip, like I don't want to tell my logic everybody, just I will tell them you can use my IC using this interface. What is that interface means? That interface is a called protocol. Okay, that could be a APP, AHP, anything. So you can use one of these interfaces to establish a communication between this processor and this memory. So you are successful in doing this. Now you establish a connection between the processor and the memory. Now, so what your code is telling to the processor means you write something to this to this IC using this I2C ASIC. So how you gonna talk to this I2C ASIC? You have to establish one more bus over here, and that bus is the AHP bus or APP bus. So this APP, AHP, AXA, all these are like talking within this only single die. Okay. Whereas coming to the I2C, it is coming to external to the world. Are you getting my point?
Yes, sir, getting so. In I2C we have only two wires, SCL and SDA.
Yeah, SCL and SDA.
Okay.
Okay.
That. Yes, sir.
This is like to the external world. Okay. So now how to tell that? See how my
Yes, sir.
how my throat how my food is going to inside my stomach means how it is going. There is like one interface to between my stomach and my mouth, right? So it
Yes,
is very
sir, yes,
it is
sir.
internal to my body. Okay. It is internal to my body that those are called on-chip protocols. Whereas now, if I'm using my cell phone, I'm using my hand to use the cell phone. So the hand movement is there, right? That is external to my body. So that interface is different. It is external world. These are two different things which are living apart. That interface is different interface, right? That type of interface is called I2C. Like analogy I'm telling. So they are different things. The phone and my hand are different things,
Sir,
and that protocol
yes,
is
sir.
different. Okay.
Sir, I got it. Means like to communicate on the chip, we use these ASV protocols, AMBA protocols in general.
Yeah, AMBA protocols, exactly.
And to communicate like with the external peripherals, we will have certain type of protocols like I2C and other also. So these things are used to communicate with the external peripherals.
Exactly.
Okay, sir.
See, every protocol came out based upon to build a market only. Okay, why these ARM people are developing this AMBA protocol means they're very they want to improve their market. So their market is SOC only because everybody is buying this ARM architecture and they're building SOCs. So if he don't build these AMBA protocols, nobody spend some time and they don't build their own protocols to communicate with some other ICs. That's why what he is doing means he is building his own protocols and he is selling those protocols to the people who are buying processes from them. So everything came out of upon the necessity only. Okay, I hope you understand. If you don't understand, like you can just mail me. I'll give my mail ID. Okay. So where we are now? Give me a second. So if you see,
So I have a small doubt here.
Yeah, go ahead.
So what is the difference between a normal GPIO pin and a dedicated I2C or SPI pin? Or in other ways, can I use a normal GPIO pin for the I2C communication if I've already exhausted my I2C pins?
Yeah, so let us say the processor which was the microcontrollers vendors are there, right? So they will use these GPIOs in a multiplex mode, like mux mode. So how they design their GPIOs means, so let us say they have some 8 GPIOs. Okay. So these 8 GPIOs, out of these 8, they will keep 4 GPIOs as a alternative function GPIOs. So alternative function GPIOs means what they will do means they will connect these 4 GPIOs to the different peripherals. What means at a time you can use these 2 GPIOs to act as a spy for spy, or at a time you can use these 2 GPIOs as I2C pins, or else if you don't want to use the spy and I2C, you can use them as a general purpose input and output. And coming to the rest of the 4 GPIOs, they are like dedicated GPIOs. They didn't mix these GPIOs with any other alternative functions. So how you can do all those things means, earlier we talked about registers, right? So the configuration registers and data registers. So they will give whenever they're designing some microcontrollers, there will be some there will be some architect. So what they will do means, they will target only one domain of the people. So they will target one applications. They'll target few applications. So if they are targeting with the mostly to the external world communications with the chips, with the external world chips, they will give more importance to these I2C protocols and SPI protocols, and they will allocate more GPIOs to function as the I2C pins and the SPI pins. Okay, that is nothing but what they will do means, here you will have GPIO block, you will have I2C block, you will have on SPI block. Okay, SPI, I2C, and GPIO. So let us say, let us think only 2 pins. Okay, our microcontroller is having only 2 pins. So what they will do means, here there will be some registers. Okay, so by configuring these registers, these 2 pins will be connected to GPIO with some value. Let us say if you write 01 to this register, these 2 pins will be connected to this GPIO block. If you write 02, these 2 pins will be connected to this I2C block. If you write 03, these 2 pins will get connected to this SPI block. Are you getting my point? There will be a lot of complex hardware between these things. It will not that will not be this much easy. Like, just for your information, I'm just letting you know that they can change their functionality by writing to these registers. Did you get my point?
Yeah, I got your point, but the other thing was, can I use a normal GPIO pin? I don't want to use it as a GPIO pin. I want to use it for the I2C communication.
Yeah, that
So-
feature should be given by the vendor. You can't decide that. Okay. So now I'm creating this microcontroller. I will give in my when I'm creating some microcontrollers, I will create one data sheet for that, right? So you have to go through the data sheet and you have to come to know that whether you can use those GPIOs as dedicated GPIOs or I2C pins, or you have to read the data sheet. I will if I'm using them as if I design those pins as dedicated GPIOs, you can't use them as I2C pins. If I give you a feature that, hey, you can use these 2 pins as I2C also, like you just configure this register, write 02 to this register, then you can use these 2 pins as a I2C pins. And there is another vendor, he is not interested in I2C, just he remove that I2C block. He will in his data sheet, he will say, my microcontroller doesn't have any I2C interface. If you want buy. If you don't want buy, just leave and buy another I2C, another microcontroller. He will say like that. So are you getting my point? Now your application wants I2C, you want to use those GPIOs I2C, right? So you have to find a microcontroller which a vendor who is providing that kind of interface. Did you get my point?
Yes, I got it.
Got
Yeah,
it?
like in my case, I was using my requirement was to use 4 I2Cs, but
Mhm.
my controller had only 3. So I had used one GPIO for the I2C, whereas the programmer wanted me to change the microcontroller itself.
Yeah, you have. If you want 4 I2Cs, then you have to change the microcontroller. Like, you have no option.
Okay.
Okay. So we got a point. That's why I'm just bringing to your notice. That's why
Yeah.
these days, a lot of embedded applications, they are moving to the FPGAs because these FPGAs doesn't have any limitations. They have one limitation, which is called resources. Okay, so you can fit a lot of I2Cs in that. Means you can code an I2C master in Verilog. You can just build an IP and you can instantiate those IP how many times you want. You can instantiate those many times in your top Verilog code, and you can just generate bit file and configure that FPGA. It will act as a 4 I2Cs then. Did you get my point?
Yes, I got it.
Yeah, but the FPGAs are too much costly. That's why we just limit our things with the microcontrollers. Okay.
Yeah.
Maybe in future FPGAs can be cheaper, can get cheaper, then we can use. Okay. So I told you, right, this is the start condition that SCL is high and this SDA changes from high to low. That thing is treated as a start condition by the target. And coming to the stop condition, this SDA should change its state from low to high when the SCL is in the high state only. Okay. This is the start conditions and the stop conditions. So how this I2C protocol works? Here, start command. So it is this start is 1 bit, target address is 7 bits, read or write is 1 bit, target register address is 8 bits, data is 8 bits, acknowledgement and stop is 1 bit. Okay, I'll just ask you one question. Like I told you, right, we can use a single controller and multiple targets, right? So maximum how many targets we can use to a single controller?
Uh, 2 raised to 7.
128, sir. 2 to the
Yeah, 2 to the power 7 because the target address is 7, right? But there will be some reserved address. Just now we are talking generically, right? So you can connect the 128 targets to a single controller. Okay. So, and one more important point in this I2C is at a time, you can send 1 byte of data only. Okay. So when so initially we'll send a start command at the time of start. All these targets will come into the active state. So they are just listening to the master, listening to the controller for the address. So one of our constraint is we have to send only 8 bits, right? So after the start command, what we do means, so like what I2C expects means, we have to send the target address concatenated with the read or write bit. So what does it mean means, so we have to send the 8 bits of data at a time, right? So what it does means, it will concatenate the whether if it is a read transaction, it will just write 1 over there. If it is a write transaction, it will write 0 over there, and it will concatenate that read or write bit with the target address, and it will send all the 8 bits at a time. Not at a time. It will send serially. Okay. So here, if you see here, first bit, second bit, and so on. After 8 bit. So the first 7 bits are the target address, and the 8th bit is the read write bit. Okay. Everybody is with me?
Sir, what is this target address and target register address difference?
Okay. So when we discuss this GPU expander concept, the registers, what are the registers having in this GPU expander IC are called as the target register addresses 0, 1, 2. Okay. And the address of the GPU expander is called as a target address. Are you clear?
Address of GPU expander or address of those slaves?
Address of the GPU expander is called as a target address, and the address of the registers which are present inside this GPU expander are called as a target register address.
Okay, sir. Then how it will be like? How it will communicate with those slaves? Like, how the slave know that the data sent is for that slave or not?
You'll come to know that in the next slide. I'll just let you know. Okay, I'll explain the next slide. Okay.
Okay.
So now what my intention in this slide is like, you have to know that at a time we have to send 1 byte of data. Okay, after sending 1 byte of data, you have to wait for the target response. If it is send the acknowledgement, meaning that the target received those 8 bits. If you don't get the acknowledgement, like acknowledgement means target pulls that line to low. Okay, if you don't receive the acknowledgement, means the address which was sent by to you doesn't match with any of these targets. I will explain you in this way. As I told you, every target will have 7-bit address, right? So let us say this target is having address as 00100. Okay, and this address
Target
is,
address is of GPIO expander now.
yeah, like target address means I have taken as a GPIO expand as one of the target. That those targets, see here, IO expanders, LED blinkers, LCD driver, temp sensor, all these are the target address only. Like all these are targets only. Every target will have a unique address. See, for this IO expander, we have 001 000 as the address. This LED blinker I have 0100 000. This is one of the targets.
And sir, inside all these slips, there will be register. So that's why you wrote register address.
Yeah, the name of those things is target register address.
Yes, sir.
Okay.
Okay, sir. Got it.
Okay. So whenever the microcontroller sends the start command, so all these targets will be in a listening mode, and they will receive this 7-bit address. Okay, and they will match this address, means they will match those 7 bits with the address encoded in their chip. Okay, so these ICs know what their address is. So they will compare this data with their addresses. If the address match, that signal will send the acknowledgement to this controller. If the address doesn't match, they will not react to that controller. Okay.
Yes,
Everybody
sir.
is
Yes, sir.
clear? Okay.
Yes, sir.
So that is, see, if you observe, after every 8 bits, you are having one acknowledgement. After every 8 bits, you have one acknowledgement. Okay. So when the transaction is completed, it will send stop. Stop means whenever it is high, it will just go from low to high. Okay. It will send stop, or it will send repeated start. Repeated start means again when the SCL is high, it will go from high to low. This is the start and stop conditions. So now I'll show how the write works in the I2C protocol. So first here we'll send a start address, like start command. So first, like start command means the SCL will be high and the SDA will change from high to low. This is the start command and this is the start command. Okay. After the start, this A0 to A6 is the target address. A0 to A6 is the target address. Now we are writing, we are in a write, we are just doing a write transaction, right? So here I'm writing 0. That's why it is called W bar, indicating that whenever you write 0 over here, this transaction gonna be a write transaction. If you write 1, this transaction gonna be a read transaction. Okay. After sending this 8 bits, the target waits for the acknowledgement from the the controller waits for the acknowledgement from the target. See here, first send start bit, send target address concatenated with the read write bit, and wait for the acknowledgement. So this is the acknowledgement which will be sent by the target and which will be received by the controller. So if acknowledgement is received, jump to the step 4. Means if you got the acknowledgement, just go to the step 4. If you are not, if you didn't receive any acknowledgement, just go back to the step 1 again. Okay. So what is in step 4 means? So now you got to know, let us say now you want to talk to this IO expander and you send the let us say this is not IO expander, this is the GPIO expander. Okay. So you send to this you send the GPIO expander address, and the GPIO expander reacted to your address. So it send the acknowledgement. So now what you want to do means you have to configure those GPIOs as inputs or outputs. Okay. Sorry, you have 8 GPIOs, right? Like here you have, here let us say, sorry, here we have 4 GPIOs, right? And here for your understanding, I have taken the 4-bit registers, but in reality there will be 8-bit registers only. Register size will be 8-bit. that is fixed. Okay, for your understanding, I have taken 4 over here. So now you want to configure the 8 GPIO hours whether as input or output. For that, you have to write to this configuration register, right? The address of this configuration register is 1. Okay.
Do the experiment like practice on this protocol? Do we need any kind of software? Like we can write Verilog code for on software, but these protocols, what we require?
So like there will be like 2 things. How means if you want to understand this I2C protocol, how it works means like if you want to understand the sequence of steps of this protocol, you can just buy any microcontroller like for $20 you can like for almost 1500 2000 you can get any microcontroller, and you can buy any ICs this type of GPU expander. It will cost around 100 rupees or 200 rupees, and in lab you can just I already told like one of the guy asked right to which GPIOs I should connect. That for that information you have to read the data sheet. You know, like all these protocols and everything are not a big thing. They are like very you don't want any more electronic background also. If you can understand like if you can read and analyze something, these protocols are very easy. So for that, you have to refer all the websites as a reference only. You just don't rely on those websites completely. After this class, you just don't believe me what I said. You just go to the website of the vendor. Like you know, this I2C protocol is created by the NXP Semiconductors. You just go to the NXP Semiconductors and you just download this I2C protocol data sheet. So there you can find the what this I2C protocol means and everything. So here 2 things. Now you have the I2C protocol spec which was given by the NXP, and you have the I2C protocol of the microcontroller. Okay, so the microcontroller protocol is data sheet is necessary for the people who wants to use the I2C protocol. Means just they use this I2C protocol and just they establish a communication between a chip and a microcontroller. And coming to this NXP semiconductor data sheet, this should be needed by the person who is gonna design this I2C protocol. Means the microcontroller vendor will take this I2C ASIC, right? I told you, right? So this thing has to be designed by someone, right? Those people will design in Verilog only. And the person who is using microcontroller, he use the any high level language C or C++. So if you want to experience how I2C protocol works, you use a microcontroller. If you want to experience how I2C protocol is designed, you have to use an FPGA.
No, we just want to prepare for the interview. Then we need to prepare it for theoretically only.
So if you need to prepare theoretically how it works means, then you can buy a microcontroller and just an IC like GPIO expander, any temperature sensor. Like you will have a lot of things which is having an I2C interface. In lab, you can just connect 2 GPIO pins.
Sir,
which is
in
having
Arduino also, no, it is I2C protocol they are using for communication.
actually, I didn't look at the Arduino till now. If you want, I can just see and give me a second.
Sir, and another question, how like the question will be on this I2C protocol will be asked in interview?
So how it will be means like it depends upon the role. So how they will ask means
Right, for design and verification if we are going then?
if you are going for design and verification, the interview will be very interesting. So how they will ask means so in how many states you can implement the I2C master, like I2C controller. Like there is a sum of sequence like start command, send the target address along with the read bit, send the data. I'll just cover what to send of the target address. So to do all those things, you have to build an FSM. Okay, So in interview, probably how they will ask you means, so in how many steps you completed this controller code? So how you manage it to, how you manage to write the data? So these type of questions comes to designing part. And some more questions like they'll come to the timing part also. So how you achieve this timing? So how you interface with this the one which you design? Like they'll if you say in your resume, most of the companies what they do means they will ask from your resume only. So if you write in your resume that you have designed I2C and used that I2C, they will ask you how you design and how you used it. If you write only design, you can just they'll ask you how you design. And if they ask you, did you verify that I2C? You can say no, I don't have any feasibility to verify that. I am limited with the resources. So that's why I did a simulation. In simulation, it worked. Like that, you can just tell them like that. Whereas coming to the embedded targeting resumes, like embedded targeting companies, there they will ask you like how did you write that function. Like they'll mainly concentrate on how you write those functions, like
Function in which language we write function? C.
yeah, in C, embedded C,
Okay.
you have to write those functions in embedded C. Usually what these microcontroller people will do means, microcontroller vendors do means, just they will let you know the registers of all those I2Cs, and just they will give the data sheet and everything to you. So you have to read the data sheet and you have to code that in a embedded C. Like you have to create functions like I2C write, I2C read, those type of functions you have to create, and you have to write and read to those I2C chips.
Okay, so coming to the design, like how do we design it in Verilog and how do we verify it? Like I don't get the idea because it is a protocol, it has wire and it sends data. So how like exactly we design it? How do we verify it?
So do you have any FPGAs in your lab or somewhere? Do you have any
No,
FPGAs in
sir.
your
No,
lab?
no, sir. No, sir.
So like what you can do means, do you know how to use Model Sim or Vivado simulation tools? Any
Yes,
simulation tool?
sir. Yes, sir. Yes, sir. Those things.
You know, right? So first, what you can do means you can just download that NXP semiconductor data sheet, which is having I2C protocol information. Okay, so you just go through the waveforms. So the main part in designing is like you have to understand the waveforms which was given in the data sheet. A lot of people do a mistake out there only. They don't understand the waveforms and they'll mess the complete code. So first, what you have to do means you have to develop an FSM. Okay, so FSM is nothing but states. So what is the state? Start state. Okay, so first of all, it will be in a reset state. So first, after the reset state, it will go to the start state. After going to the start state, it will go to the target address state. Okay, after target address state, it will go to the data state. In between, there is a one state which is called the acknowledgement checking state. Okay, are you getting my point?
Yes, sir.
So you first of all you have to develop the FSM. FSM is the crucial part. Whenever you are designing something, just don't start any code. Like if you have a let us say you have 100% of time, in that you have to use at least 40% of your time to design your FSM only. You have to verify, like you have to think in a different ways. You have to read the data sheet. You have to think in a different ways. Okay, in data sheet they will give each and every constraint. The data sheet is like a very packed thing, so they will give each and every constraint in that. So you have to read that constraint and you have to verify your FSM whether the FSM is following that constraint. Okay, if it is following, just go through, and you have to re-verify the FSM. Once the FSM is logged, you have to start coding in Verilog. Okay, so once you completed the Verilog coding, you can just verify in the simulation.
Sir,
Did you get the point?
sir, so we are coding like in FSM this I2C master. So how this
Mhm.
master will work? Is that right, no, sir?
Yeah, you can code I2C master or I2C slave. It's up to you. If you want
Sir,
to say right.
how we will code like input output or those things, because those contain registers, and in Verilog we just generally deal with digital partner. So
So okay, give me a
like
second. I'll just explain you.
yes, sir.
Mm. Everybody can
And
see
this
my slides or no?
no sir, no sir, not.
Yeah. Okay, give me a second. Now?
Yes, sir, visible, sir, screen visible now.
Mm. So first of all, you'll have only two ports in your Verilog code also, right? You'll have in Verilog, you'll have a module, and this module will have only two ports. Okay, in that one port is SDA, and this is the inode port. Okay, and the other one is SCL port, and this is the output port, right? So you'll have SDA port and SCL port, right? So
Yes, sir.
earlier when I told you, you have to write only 0 and Z. Okay. Did you follow the class from starting onwards?
Sir, in starting I joined late, sir. It was like yesterday it was told at 10 a.m. your class is there. So you
Okay.
like 10 minutes, 15 minutes is late.
Okay, I'll just do a quick review. So
Yes,
there will
sir.
be a pull-up resistor over here. So this will be always 1. If you want to pull down this, there will be one transistor over here. Okay, and whenever you write 0 to this transistor, it will form a closed loop, and there will be a 0 at this point. Okay, if you write Z to this, there will be a 1 at this point. Okay, so in I2C you can write only 0 or Z. That's all. You can't write 1. Okay.
So Z means high impedance.
Z means high impedance. Yeah. For whenever you are using an SDA, whenever you're using an inode port, whenever you are
Sir.
not driving that port, you have to put in a tri-state, right?
So for making it high impedance, like we have to open this transistor, na? For opening this
Yeah.
transistor,
You
we will give
just
one
don't write
and
anything to this transistor. It will be in off state.
that I have not like if you will give one, it will get open circuited and the high impedance will form here.
So like so whenever you write this type of code, like I'm telling in a perspective of the FPGA side, okay, because like I'm an FPGA guy and I don't know how it will be done in the ASIC side. So in FPGA, how it works means whenever you write in a in-out mode and whenever you are driving Z, okay, there will be a primitive called IO buffer primitive, okay. So whenever you are declaring a port as in-out, the tool will sense this in-out and it will instantiate this buffer automatically. So this IO buffer will act as output and input and both. That is some complex concept. Okay. So you just imagine like whenever you don't want to use that bus, write Z. Whenever you want to use that bus, like how usually we code means we code everything in 1 zeros only in our code. All FSM goes in 1 zeros only. There you will write some two combination statements like assign SDA is equal to Z when you'll take one copy of this SDA inside your code like SDA buffer, like SDA copy, anything, any name, what you use inside. So you like SDA is Z when SDA copy is equal to 1, else 0. Are you getting my point?
Yes, sir. Somewhat getting, sir. What you're trying
Yes.
to-
So what I'm trying to say is, see, like whenever you are coding in your Verilog, so you just take two signals, SDA CPY, SCL CPY. Okay, you write your logic completely with this using this SDA CPY and SCL CPY, and you complete everything. Now you are treating just one and zeros, one and zero, one and zero, everything one and zero. You are just working with ones and zeros only. Now, when you are sending it to the external world, like you have your Verilog module with the SD and SCL, right? So now what will you do means this SDA, this is like assign SDA is equal to Z if SDA CPY is equal to 1. Okay. And 0 when this SDA CPY is equal to 0. Else Z. In the same way,
Okay, sir.
assign SCL also this same logic for SCL also. So now here what you are doing, when you want to write 0, you are writing 0. When you want it to be 1, you are just you are releasing the bus. Releasing the bus means what is happening? You are deactivating this transistor, and you are releasing means it is automatically pulled high, right? It is automatically pulled to 1, right?
Yes, sir. Yes, it will be
So
pulled
you
to
are
1.
not writing 1, you are just releasing that bus. It is automatically going to 1.
Yes, sir. Yes,
Are you getting my point?
normally it is in high state. It's high.
Yeah, normally it is the highest by default. So
Yes.
when it is already in high state, you can't tell go in high state again. So if you don't want to send the high, like if you don't want to send 0, just leave the bus. It will go to high automatically, not automatically because of this connection interface, external interface.
Okay, sir. And here SCL is clock now.
Yeah, SCL. You know, this is a tricky. This is somewhat tricky. You know, so this is not a continuous clock. First of all, okay.
Yes,
This
sir.
clock will be activated only when the transaction is there. And
Okay, sir.
one important thing is like not important thing that is like a some kind of interesting stuff. So now you are using the bus, right? So now you are using the bus and you are just sending the clock, you're sending the clock, you're sending the clock, and you are expecting a acknowledgement from after sending 8 bits, you are expecting a acknowledgement from the target. Okay. So the target will send the acknowledgement on like the target will receive data or sends data on the raising edge of the clock only. Okay. Let us say if you don't send raising edge, like after this you are sending all the time low means it will just wait for the raising edge. It will not do anything. So few people say that then it is not called as a clock. Few people say that like that is a clock, but not a clock. It's like a famous dialogue. It happened never before, but it happened like that. This is a clock, but not a clock exactly. Or in real world, if everyone will say clock is a continuous with 50 megahertz duty cycle, 50 megahertz duty cycle. Whereas in I2C, clock is generated by the controller when it is necessary only. If it feels there is no requirement of clock, it will just seize the clock.
Okay, sir. So it
Okay.
is so it is a reference signal on which like data will be assigned only at the process of this
Yeah,
whatever is
it is like
clock.
a reference signal.
Yes, sir. So it is a synchronous then communication, asynchronous.
Yeah, that's why like because our data is just the movement of our data depends upon this raising edge of clocks only, right?
Yes, sir. Yes, sir. Okay,
Yeah,
sir.
that's why it is synchronous.
Okay, sir.
Actually,
So
if you start developing this code, at some point of time you will realize that you have to release the data on the falling edge. It will latch on the raising edge by the target. So you will get to know this point when you start developing the code only. You will not get this why I have to send this at falling edge means there is some interesting topics of the timing. Okay.
okay, sir.
This is there will be two types of usage of this protocol. Some students wants to work on embedded applications. So for them, I2C is nothing but like just a piece of cake. Like just they can understand the protocol and just they can develop C functions. That is not a big deal. But the one who developed this I2C, like they are the luckiest guys, I can say, because they just go deeper and deeper, and they'll get to know. They'll just you can feel that happiness when you design the I2C. First of all, you have to use the I2C, and you have to know how it is working. Then you start designing it. Then you can feel that, oh, that's why it is happening like that. Oh, that's why this is happening like this, because inside circuit is like this. It will take time. Okay, just don't worry, everything takes time, but you have to learn it very carefully in a small amounts. Just don't try to think I have to develop the I2C protocol in this week. Just don't think like that. Just allocate some part of time every day for I2C protocol, and you just develop FSM every day. Sit for 10 minutes, or 20 minutes, or 25 minutes. Just complete one block of like one state in the FSM. So after some time, after some days, you will just but you have to sit every day. If you skip the day, just you will lose your coherence over there. Okay, that's why what I
Yes, sir.
suggest for the designing people is you have to understand the I2C very, 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 very well. What I suggest to the embedded people means just you have to know how those things works, like what are the steps you have to follow. That's what I can suggest. Okay.
Okay, sir. Okay, sir.
Any other doubts?
Sir, one more doubt. Like during the communication, like we are sending zeros and ones. You said like to start the transfer, we will send zero at SDA pin. Okay, sir. So
That is start command.
and to stop it, we will send one.
Yeah.
Okay. So
Yeah.
while during sending those address bits or other bits, so at that time also it will transition to one. So how will it like differentiate between, is it
That
like
is
a
like
stop bit?
that's a good question, which I got during my earlier stage, but it will not happen at that time. If you see, like this is the SCL, right? And your SDA is going from high to low, right? Okay.
Yes, sir. Yes, sir.
Now after this, what will you do? This is the falling edge. Your SCL will go low, and your SCL become high over here. So whenever it is, I told you, right? At some point of your development, you'll come to know you have to release the data at the falling edge of the clock.
Okay, so release the data at the
Yeah.
release as in sense means it will transition from 1 to 0, high to low.
Yeah, when the clock is transitioning from 1 to 0, you have to send the one MSB bit over here. Whether it is 1 or 0, you have to send it on the SDA. Okay, and this shouldn't be changed until next falling edge. So what happens? Let us say you are sending 0 1 0 1 0 1 0 1. Wait, I'll just draw it very neatly so that you can understand very well. Okay, so here first data will be low. Okay, so this is start condition. Okay, now at the falling edge, what will you do? You will send 0. Okay, so 0 means this 0 shouldn't change until this falling edge. This 0 shouldn't change until this falling edge. So now you are releasing the data at the falling edge. At this edge, the target samples the data at the raising edge. I told you earlier, right? The target samples
Yes,
the
sir.
data at the raising edge. So
Yes,
here it is 0, right? So it will treat it as a 0. Now what it will do? Now what will you do at this falling edge? You will change the data to 1 because this is 1. Okay. Now this 1 will not change until the next falling edge. At this raising edge, target will sample it as a 1. Okay. And at this falling edge, you will again change it as a 0. You'll not until change it here. Change it to 1. Change it to 0. Like it happens. So at every falling edge, you change the data. At every raising edge, target samples the data. Okay.
Okay, sir.
And one more thing is like to generate this scenario, your clock, like your main clock should be higher than the clock rate at which your I2C works.
So main clock frequency should be higher than this clock frequency.
Yeah, then only you can just change these two things at a time, right?
Okay, sir. Okay, sir.
So at least your clock should be the double the required frequency of the I2C. Okay, then only you can generate this type of scenarios.
Okay. So, sir, my question was like when it is transitioning from 0 to 1, so it is 1 in SDA is 1. So how will it distinguish that it is an address bit 1 or is it a stop sign, like to stop the...
I will just explain the next slide. There will be some pattern. So how it works means after one state, it will the target will expect. So after sending the target address, next it will expect the register address. Okay, I will show in this waveform. See here, you are sending the target address, right? So after sending the target address, target will send you acknowledgement, say that, hey, I am here. Like I am here. Okay, you don't worry. You can send now whatever you want to send me. So then let us say our GPU expander responded to the controller by using this target address. So after sending this, our GPU expander sends the acknowledgement. After that, now you want to configure the inputs and outputs of those GPIO. So you'll know like let us say out of this 8 GPIO, let us say we have 8 pins. Okay, 1 means output, right? Let us say we want to configure 1 pin as output, input, output, input, output, input, like the 10101010, right? So that register number is 1 over here. Configuration register number is 1. Okay. So now what will you do? Your target register address is now 1. So you will send 1 in these 8 bits. So now you will send 1, like 1 means 000000001 means now you are telling to the target that I want to write the register 1. Okay. Then it will send an acknowledgement saying that, okay, now you want to write to the register address 1. That's fine. Okay. Now you will send the data now. So what is the data of that configuration register? We already told that 1010101010 is the data address, like data of the data register. So after sending this register, like after sending this data, it will sit in that register. And now all the GPIOs will be configured output, input, output, input, output, input. And after, if this transaction is successful, it will send again acknowledgement. Now your process is done. Like you are successful in writing the one of the registers. Now you want to stop your transaction. Then you will send the stop signal. How will you send stop signal means? First you will make the SCL high in your code. You will make SCL high. Then before making this SCL high, you have to make sure that your SDA is low. After that, you have to make this SDA to high. So this condition is treated as a stop condition. This condition is treated as a start condition. In the middle, no transaction will be done like this. Everything will be done on the falling edge or raising edge. No transaction will be done on the level edge. That's why you will not have any issues in the middle of the transaction. Like nothing will be detected as a start or stop. Everything is that's why I told you have to develop an FSM now, thinking that okay, first is the start state, next is the address state, next is the register address state, next is the data state. Are you getting my point?
Yes, sir, getting, sir.
Like if you have anything, let me know. You are asking good questions.
Okay, sir.
Like any doubts you have?
Sir, right now.
Okay, I'll just move on. If you have anything, please stop me. Okay.
Okay, sir, sure, sir.
Okay, now the read part is little bit complicated than the write part, but it is some interesting part, and you can come to the what is the benefit of repeated start also. So initially, let us think like we have 3 registers, right? 1, 2, 3. So during the write transaction, what did you do? You have returned to the register 1. Okay. Now you want to read the register 3. Whatever is the data, you don't care about the data what is present in 3. Now you want to read the register 3. So here what this protocol is expecting means, first you have to write the target address in a write mode. Then after you send the register address. Okay, you just break it into 2 parts. So first of all, what it is expecting, first write the target address and write the target register address. If you don't have this part, like if you don't have this write transaction, like if you don't have these 2 parts, and if you start directly these 2 things, means first of all writing this target address, and if you read the data, what it will return means it will return you the first register data, because in the previous transaction what did you do? You wrote to the register 1. So there will be a pointer in the target, so it will be pointing to the register 1. So if you send directly the read command, it will return you the register 1 data only. To avoid that, what you do means, first you set that pointer. That's why they are telling that first you write the target address with the right bit, then you set the register which you want to read. Okay, then you set the register which we want to read. Now what we do means, I first write the target address and I will write 03 over here. Then I will just do a repeated start and I will write target address again, and I'll just read. I'll just send the read signal over here. Now it will return me the 3rd register data. If I don't write this part, if I don't do this part, and if I directly do this part, it will return me the register 1 data. I know it will be confusion. So now what confusions you have, let me know. I will explain you very clearly.
Sir, I am on.
Hello.
Hello.
Yeah, please go ahead.
Yes, sir. Sir, if we send address once, then why we need to send again the same address?
No, like what I'm telling you is, earlier we did the right transaction right here. Here what we did, we write the data to the register 1. Okay. Now we want to read the register 3. Okay. So after doing the right transaction, now the pointer will point to the register 1. Okay. So now if you don't set the pointer to the register 3, and if you directly initiate a read transaction, it will just return the register 1 data only. But you are expecting register 3 data. So for that, what you have to do means, first you have to set the pointer to register 3 by using the right transaction. Okay. See, if you observe here, you are not writing any data. Just you are setting the register address, and you are sending the repeated start again over here. And you are just repeating the whole scenario. Okay.
Okay, sir, got it.
Okay. Any other doubts? So before that, I'll just write my mail ID. If you have any doubts, you can mail to this ID. Okay. Just expect 1 day delay. Okay. So maybe if you send me in the morning, I'll try to give the reply within 12 to 24 hours. Okay.
Okay, sir.
Just like I
And what
Hmm.
are the resources we can refer to like learn more about this protocol with
Uh,
respect to our preparation, not like in research?
so what you can do means like you can just take any one of the microcontroller data sheet. I suggest you to take Texas Instruments because like I work with them a lot. That's why I'm just telling you to take any Texas Instrument. So you can just open the data sheet. You can take this data sheet and you can just go to the I2C section. Okay. And you can just read it and you can just see the waveforms. If you want to know more also, you can just refer to the Jink 7000 TRM. These are the resources I am suggesting for the people who wants to use the I2C protocol, and for the people who wants to design the I2C protocol, you guys download the NXP. Wait, I have taken one image from the NXP. So you can just download this data sheets UM10204. Okay. And
Okay,
these are
sir.
these are thing I have referred one of the uh, TI documents. So the what I suggest for the designers is you just go to the original documents and you use the remaining websites as the reference only. Okay, you just don't rely completely on the third-party websites. You just use third-party websites to understand the terminology. You just focus on the parent company documents only. And the one who wants to target the embedded applications, you can find a lot of third-party websites explaining how this I2C protocol works.